OK， 仲未開而家。點呢個？邊個先？你嘅書幾鬼用？而家都有間好好嘅 coffee shop， 一間好好嘅 coffee shop， 書名大過書名最大個，書名最大個咧。哇！而家呢個呢最全個 camp 最好嘅 camp， 即係個 object 個特色，有啲原檔嘅嘛，係咪呢種？佢從佢開車咁樣開上去，咁就知我講啲嘢。12分鐘。
好，今天是用英语演讲It's a great pleasure to have Professor Kenneth Young with us today. Professor Young received his PhD degree from Caltech back in 1970s, and now he's a professor emeritus in Chinese University of Hong Kong, and he's going to give us today the title of the colloquium is Optical Tweezers and Ponderomotive Force. Let's welcome Professor Young.
Thank you very much for the kind invitation and giving me this opportunity to visit Tsinghua University once again. I was just thinking back when was the first time I came to this university. I don't know whether it was in the late 70s or early 80s, but a long time ago. And I had the opportunity earlier today of meeting Professor Ed Yan, who's, I guess, the older members would know, a very venerable member of your department, now retired. And I look forward in a couple of hours to meeting Wei Dou, who perhaps again some of you may know. Wei Dou was my contemporary in many ways. Okay.
So you have overlap with Wei Dou?
Oh yes, we were about the same time. And if I remember correctly, he was my TA in some course, quantum mechanics or something, but we were contemporaries. Anyway, so hope to spend the next hour or so talking about this. This is a rather unusual topic, And this is just a repeat of a talk I gave in my own department late in last year, 2018, soon after the announcement of the Nobel Prize 2018. And it just so happens I know something about that topic and have done something sort of tangentially related. So I thought at that time I would make up a talk introducing some interesting topics and remembering some of the work we did ourselves, sort of in relation to these topics. So the 2018 Nobel Prize in Physics was given in two parts, both for some sort of laser physics. And I'm going to talk about only, these two worked on high-intensity ultra-short optical pulses, but the other half went to Arthur Ashkin for optical tweezers and applications to biological systems. And I'm going to talk about that half of the Nobel Prize awarded to Ashkin. So that's Ashkin, born 1922. He was 98 at the time he won the Nobel Prize. He is the oldest at the time of winning the Nobel Prize, ever. Any Nobel Prize, I think. Okay? And he said, I'm not going to broadcast this. One thing you need to do to win a Nobel Prize, necessary but not sufficient condition, is to stay healthy. If you don't, at least in his case, if he didn't live to 96, he wouldn't have won the Nobel Prize. So stay live to 96. I didn't realize I'm the oldest ever, so I just about made it. Because you can't be dead and win. So that's what he said. Okay, so this is the from the Nobel citation. He was awarded for inventing optical tweezers using optics that grab particles, atoms, viruses, and other living cells with their laser beam fingers, and this knew to allow Ashkin to realize an old dream of science fiction, using the radiation pressure of light to move physical objects. Actually, the Nobel citation is not quite right. It's not really radiation pressure that moves things around, and this is one point that I will talk about. So he succeeded in getting laser light to push small particles towards the center of the beam, and this is the correct statement, and to hold them there. Optical tweezers have been invented. So let me just start off by telling you the difference. If you have a beam of light like this, like the beam coming from that projector, radiation pressure is a force in this longitudinal direction. Whereas this is a force in the lateral direction, holds particle towards the center of the beam. And that's the distinction, one of the distinctions I will talk about. So this was again from the citation. I think major breakthrough came in 1987 when he used the tweezers to capture living bacteria without harming them. So what was our intersection with Ashkin and this kind of work? Well, it turns out that my colleague Lai and I, as early as 1976, this is our paper in Physical Review A, response of a liquid surface to the passage of an intense laser pulse. And this is from the abstract, all right? The temporal hydrodynamic response, blah, blah, blah. And we found in satisfactory agreement with the recent meaning recent with respect to 1976, experimental result of Ashkin and Dipole. So Ashkin, so we sort of had an early encounter with him in 76, before most people here were born, right? We tried to answer the question of momentum of light in material medium. So this is what I will talk about. First of all, part A, the role to optical tweezers, at least from our point of view, some of these issues. And then part B will be some of the theoretical subtleties which we elucidated in the course of quite a number of years. Okay, so first of all, the role to optical tweezers. Now, I'll just remind you of third year, I suppose, electrodynamics. If there is a plane wave, then there's a pointing vector, S, which is proportional to E cross B, right? Depending on what unit you use. Pointing vector is the flow of momentum, and there is a momentum density, which I call little g, it's also E cross B. In suitable units, they are the same thing. They are sort of like T0I and Ti0, symmetric energy momentum density. the question is, this is what happens in vacuum. What about in a material medium? Suppose you have an electromagnetic pulse propagating, let's say, in water. All right? So what would happen to these quantities? In particular, what would be the expression for the momentum density? Well, you all know in the dielectric medium, probably you just replace E by D. You know what D is, right? The displacement vector. So the E plus a polarization term, right? Or in terms of a linear dielectric, D and E differ by a factor of the dielectric constant, basically. Okay? So Minkowski, the famous Minkowski, proposed that the momentum density of light was D cross B. Another guy, Abraham, said it was E cross H. There was a big controversy over many years. What is the momentum of light? What's the momentum carried by a pulse or plane wave propagating in a material medium? So what is it? Okay. So there are many ways of trying to get at this problem. Many people have worked on it. Minkowski, you know, Abraham, Einstein worked on it. Taub worked on it. Okay, and I will tell you they're all wrong. Okay, so this is a nice problem to work on. Even if you get it wrong, you are doing as well as Einstein. Okay. So people say maybe T mu nu should be symmetric, right? Fundamental principle. That's actually not a good argument. You know why? Because when you say symmetric, you are using ideas of Poincare invariance and that sort of thing. But if you're in the dielectric medium, there is a preferred frame, the frame in which the medium is at rest. So most of your usual ideas about invariance actually cannot be applied. There are people who sort of manipulate formal expressions like this one, which is time rate of change of the momentum density. If I have a volume, the amount of momentum in this volume is changing for two reasons. One is because there is momentum flowing in through the boundaries, and that is given by the divergence of the stress tensor. And then secondly is because somebody is acting on it with a force. So that's just a conservation law that must hold. So if I know any one of these three terms, then I can sort of deduce the other two. So you really want to deduce this one. So if I know either this one or this one, most likely this one, maybe you can get at it. So there are people who sort of use this, write down what they think this is, and try to work it out. And I'll tell you later that this, at least as usually handled, is also wrong. You can't manipulate that. So why is it wrong? Well, let's review how you handle a material dielectric. So there is polarization, P, which gets embedded into D, right? D is basically E plus P with some constant depending on the units. And divergence D is the free charge. Not the total charge, but the free charge. Now, how do you do averaging? For the stress tensor, well, this force on a bit of the dielectric looks something like this. The dipole density interacting with the gradient of the electric field. Right? P dot gradient E is the force on the dielectric. So up to moving some derivatives in and out is essentially derivative of E times D. So, and E times D is basically something like the stress tensor. So this is the divergence of the stress tensor. So in a dielectric medium, you want to average this thing over space. You don't want to look at individual atoms. You want to look at a volume containing many molecules. So you're averaging a quadratic expression. The average of a quadratic expression is not the product of two averages. Okay? There are fluctuations. And this is where most people get it wrong. And this, another way of saying it is that this P does not see the average E. If the P sees the average E, then I can average the two factors separately. But P is correlated with E. So the average of the product is not the product of the average. And that is where the problem all comes in. Now, our introduction to this problem came through a chance encounter with Rudolf Tiles. I don't know whether you have heard of this gentleman, a famous physicist of last generation. He was sort of the leader of the British contingent that in the nuclear bomb project, the Manhattan Project. If you study physics, I think there are only two German words you need to know, apart from eigen something. One is Bremsstellung, the other is Umklapp. And you know what Umklapp is? Does anybody know what Umklapp is? Do you study solid-state physics? Well, go look it up. Piles was the person who invented this word, Umklapp process. Anyway, in the early 1970s, he revived this issue, and he had a clever idea. Well, not clever, I mean, in retrospect, it's simple. I mean, it's the sort of thing you want to do. And there were experiments. And we came into contact. You know, in those days, the older members would know. I mean, this part of the world, scientifically, we were quite isolated. Can you imagine a time when there was no internet? Have the younger people ever experienced a world without internet? Where overseas telephone calls were very expensive. It's not something you do easily. And so how do you get by with your scientific contacts? You just do the best you can when scientists happen to come visiting. So Piles happened to come visiting, and he gave a talk, and that's how we got introduced to this problem. Now, so let's think about what the experiments were like. And that was how Ashkin started thinking in this direction. So he says the following. Here I have a tank of water. I have an incident beam of plane wave hitting the surface. Some part gets reflected, some part gets transmitted. So you want to know how much momentum is carried by the transmitted beam, right? But the four things must satisfy some conservation law. The momentum carried by I, part of it gets carried by T, part of the momentum is carried by R, and then some momentum is left on the surface so that the surface may move a little bit. Okay? So somehow, if I look at the momentum of the four terms, there is an equality when you add and subtract them. Now, I and R happen in vacuum, so I know how much momentum they carry. The expression for momentum in vacuum, I know. So if there is some momentum deposited on the surface would either move up or move down, right? So if I observe how the surface is moving up and down, I should be able to determine how much momentum is given to the surface. So adding and subtracting, that gives me how much momentum is in the transmitted beam. So that was the idea of Ashkin. Okay? So he just went and did this experiment. Now nowadays it's a trivial experiment. But back in those days, what you do? You have some water, you shine the laser beam down, and you observe what happens to the surface. Okay? Simple enough. Would you like to guess what happens to the surface?
Push downward.
Huh?
Push downward.
Everybody thinks push downwards, radiation pressure, right? Pushing, right? So the idea is to observe what happens to the surface and therefore determine the transmitted beam. Well, this is his paper. 1973, observed to everybody's surprise, the surface came out when you shine the laser beam on it.
Circular.
Huh?
It's a circular shape
Yeah.
around the beam.
Yeah. Okay. So that, at that time, people thought it was totally unexpected, absolutely baffled. All right, what is the radiation pressure? Okay. So this is his abstract. So he was talking about the radiation pressure, and he thought that there was a net outward force. For some reason, there was a force on the surface that was pulling it up, okay? And that should tell you something about the momentum of light in dielectric. That was what he thought he was doing. Okay, but this turns out to be wrong. This is what I will say first. So let's see, what's the correct explanation? So you see, here the purple column is the column of light. That is the region, illuminated region. The region of higher E squared. But you all know that the molecules like to go to region of high intensity. Just as, I think you must have learned this in sophomore physics, if you charge up a capacitor and you take a piece of plastic, half in, half out, the plastic will be sucked into the capacitor. So a dielectric likes to go into a region of high E squared. And therefore, the water likes to flow into the illuminated region, and because water is basically incompressible, it flows in because of a lateral force. then it just squeezes the surface out. So what he was actually observing was not a longitudinal force, either up or down. The effect to first order in epsilon minus 1 is very simple. It's actually a force laterally pushing it up. So Ashkin started with radiation pressure. He thought he was observing and trying to understand what I call a longitudinal effect, but our analysis showed that it's actually a transverse effect. And the transverse attraction towards the axis of the beam is the essence of optical tweezers. Optical tweezers is this transverse attraction into an illuminated region. There were later experiments by many others that I will talk about. So the key idea of the ponderomotive force is that a dielectric is attracted to a region of high E squared. Okay, so as I said, so if you have a capacitor and a dielectric, it gets sucked in. And the reason is the energy, this should be wiggle, goes like E times D, which is like D squared over the dielectric constant, and D is proportional to the surface charge density sigma, so sigma squared divided by the dielectric constant, the relative dielectric constant. And if sigma is held fixed, you see that if more, the region with large kappa has a lower energy. So you want to have more of the dielectric in the high field region. This problem you can analyze even, I don't know, first year, second year physics. Same idea. If you want to be a little bit more precise, it goes like this. I'm sorry, all the dots are not coming out. The force on a dipole is P dot radian acting on E. That's a standard expression. So if you work it out, it turns out to be alpha over 2 di ej ej. Alpha is the polarizability, that the polarization is alpha times the electric field. So if that's the case, you can think of the force as being due to a potential energy, it's minus radian of phi. Phi is minus something times E squared. So if you have E squared being inhomogeneous, that creates an effective potential energy, which is negative phi. So the illuminated region is a potential well, and it gets trapped into the potential well. This is assuming statics. So how do optical tweezers work? Well, this is how it works. This is the illuminated region of a laser beam right at its focus. So it's, there's a waist. And if you have a dielectric, this is the part with lower potential energy. So it's like a potential well. And this guy gets then attracted to here. And what happens is if you have, I don't know, one part, say this is a tiny plastic bead and is attached to another plastic bead, then this gets attracted to the beam as if it is attracted to a wall with a spring. So this guy is then held to the waist of the beam, and this whole thing works just like a tweezer. So that was the main idea. So this is just some random examples of what Ashkin and people did. So this is, I suppose, a cell. I don't know the details. You attach two tiny plastic beads to it, and you put a laser. So you attach one to a glass surface, the other you attach to an optical trap. That is a laser beam with a waist. So as you move your laser laterally, you can stretch the cell and do all kinds of things like this, and manipulate single cells and study, for example, the mechanical properties of cells. Okay? And in all these real pictures, the small balls are plastic beads attached to a cell. So for the first time, people are able to do biophysics with individual cells and manipulate them using optical tweezers. And so the Nobel Prize was not so much for any fundamental physics. It was for opening up this area of biophysics, single cell dynamics. So this is another thing. This is a cell where attach two plastic beads and you stretch it and so on. And they measure the modulus as a function of frequency. Okay, so you shake it at different frequency. It's a frequency-dependent modulus. So it's a kind of detail of cellular mechanical behavior that was not accessible before. Even better, if you take a DNA double strand, attach two plastic beads to the two sides. Notice in this case, the smallest plastic beads you can make is still much larger than the DNA. And you do this, and you find that this is actually the force displacement diagram. Very interesting. It goes like this. Okay? So here is a region where it changes rapidly, and here's another region where you can stretch it without much changing the force. If you think about it, that is sort of like a phase transition. Think about the following. Suppose you have water, and you plot pressure versus volume. Then at the boiling point, you can change the volume by a factor of 1,000 without changing the pressure, right? Suddenly it goes from liquid to gas. So a horizontal stretch is like a phase transition. So this kind of work tells you that DNA as a mechanical system has a phase transition, which you can study precisely. So very nice, very elegant biophysics was done using optical tweezers. Okay. So another one looking at looking at a DNA molecule. Again, this is even more precise. It's a flat region at 65 piconewtons and so on. And it turns out phase transition, these two are two different phases, two different conformations of the DNA. But what I'm interested in are some of the theoretical subtleties attending to this issue. So all this is correct for single dipole or a dilute fluid dipole. So if I understand a single dipole and have a dilute fluid, I'll just multiply by n. Okay? But what is the exact answer? And there are all kinds of controversies, and I will relate this to momentum like in a minute. Basically, is the question of what's the higher order terms in powers of kappa minus 1. Kappa is a relative dielectric constant. For something dilute, you are working only to first order in kappa minus 1. When you are looking at also including more interaction between molecules, you would be looking at high order corrections. So the Pyle's insight was the following. Well, says, hey, let's not worry about macroscopic electrodynamics. Let's go back to fundamentals. Dielectrics are nothing but a collection of point dipoles. At least that's a reasonable model. And for point dipoles, I know microscopically what happens. So let's just add it all up. So that's what he says we should do. Okay. So he says for each dipole, the force on a dipole is I'm just dropping in this P gradient E. So just add them all up. You should be able to find the force on a dipole. You know the force, then you should be able to find the momentum. Right? So go back and work with individual dipoles. And he wrote this paper in 1976, Proceeding Royal Society, basically working this out. He was a bit old at that time, actually not older than I am now. But at an age, he also didn't have any students anymore. So at that age, one tends to make arithmetic mistakes. Okay? So this paper, there were a couple of arithmetic mistakes, so his answer was wrong. In that slightly trivial sense, I mean, I got a student to look at it and found that mistake. But more importantly, he didn't realize a subtle conceptual point, which was what we fixed later. Okay. So let's try to understand what the problem is. Do the younger students know about the Clausius-Mossotti relationship? No? I was talking about students nowadays are not as well trained in fundamentals as they used to be. But anyway, suppose I have a collection of dipoles forming a fluid. The dipole moment is, of course, of each one is proportional to the imposed electric field. And the polarization density is the density of dipoles times the dipole moment of each one. So it is proportional to rho times E, right? Rho is the number density. And if that's the case, kappa minus 1 is proportional, well, kappa minus 1 is basically P over E, okay? Is then proportional to rho. So in this simple consideration, if I take a gas, liquid, gas, I can change its density. Then the dielectric constant should change with rho in this manner. The departure from unity should be proportional to the density. Okay? Now it turns out this is not quite correct. Because P does not see the average electric field. It sees what I call the local field, the field where the dipole happens to be, okay? Which I call E prime. And it turns out E prime relative to E, the local field relative to the macroscopic field, is not 1, but kappa plus 2 over 3. That is a standard problem in sophomore physics. Any undergraduate textbook in sophomore physics will have this problem, okay? And so if you take account of the difference between E prime and E, this factor will appear. And what you have is not that kappa minus 1 is proportional to rho, but that kappa minus 1 divided by kappa plus 2 is proportional. This final equation is called the Clausius-Mossotti equation, or ages old. That is how you can relate the dielectric constant of a liquid with a gas, which is just the same sort of dipoles with a different rho. Okay. Sophomore physics. Okay. Now, what do we want to do? We want to do. I want to find the force on a dipole. I said earlier it's like P gradient E. I'm skipping all indices, but no, it is E prime. So I want to find not E prime, how E prime is related to E, but how gradient E prime is related to gradient E. Okay? I need that correction factor. So what the classical Clausius-Mossotti calculation did was that you find the ratio of the local field to the macroscopic field. Now what we want is the ratio of the local field gradient to the macroscopic field gradient. So Piles did that calculation, he obtained it, and so on, and he got the answer, but as I said, minor arithmetic mistake. He did not do the more general case, he did it the plain way. So I got a student to do, not even the general case, you do the static case. Should also work if I put a dielectric inside a static electric field, right? So work out a static case with non-uniform E field. And he found something very strange, because missed a subtle point. So let's see what happens. Now, think about the following. You have a collection of dipoles, right? I look at one particular dipole. I want to find what is the force on this dipole. Now, actually, there are two forces on this dipole. One is the electrical force, which I call Fe, due to all the other dipoles and the external field. That is what Piles calculated, correct? It turns out if you just calculate this force, you find that for the fluid, this force is not curl-free, which cannot possibly be the case because in the fluid at rest, whatever force you find must be balanced by the gradient of the pressure. It can't be right. So that had us puzzling, scratching our heads for half a year. But there is another force, what I call the mechanical force, Fm. It is due to the collision by all the other molecules, right? Okay, so think of these as hard spheres, also carrying a dipole moment. So the dipole-dipole interaction is electric, but the hard sphere interaction is mechanical. But you say the hard sphere interaction has nothing to do with the field you're talking about. No, let's be a bit careful. You see, the hard sphere, the mechanical force, must depend on the two-particle density. The probability that I have two particles in a particular configuration so that they are collisions. So it's proportional to the two-body distribution. The two-body distribution satisfies the Boltzmann distribution, e to the minus beta u. Beta is the inverse temperature, u is the potential energy. U contains a piece due to dipole-dipole interactions and therefore proportional to E squared. So if I look at rho 2 and I expand it in powers of E squared, then when you impose an electric field, there is a correction term proportional to E squared. Okay? The mechanical force itself is not electrical, it's Hasier collisions. But the distribution of particles contributing to the two-particle density distribution has a piece proportional to E squared. So if I want to calculate all the parts of the force that goes as E squared, I have to include this term as well. This is the subtle point. Okay? The mechanical part of the collisions leads to an intensity-dependent force. And if you add this piece, lo and behold, the two together, the curl part cancels. Can be written as a gradient. And also, in the static case, it agrees with known. For static, everything is known. Okay, agrees with everything, and that's definitely the correct answer. So roughly, what happens is that the force on the dipole is the mechanical plus electric. The mechanical is a zero order one plus a second order one, second in E, and these two together is what we call the ponderomotive force. The part of the force which is proportional to E squared. And so this is what we find. And if you work it out, in the case of statics, the ponderomotive force is given by this expression. Gradient of the dielectric constant, U is basically E squared, and then a total gradient. Okay? Now, so inside the body of a fluid, this term is zero. This is only at the surface. So within the body, there's a pure gradient which can be balanced by the pressure. So this was published a long time ago, in 81 and 82. Okay, Physical Review and the longer version, Physical Review A, and we resolved the Piles problem. And Piles, very nicely, he wrote two books. One book after he retired. Piles was, after Manhattan Project, he went back to Britain. He was chairman of the department at Oxford and so on. Okay, so he wrote two books. The first book was called Surprises in Theoretical Physics, and then he wrote a second book, More Surprises in Theoretical Physics. And this is from the table of contents. Okay, surprises in quantum mechanics and condensed matter. Bismuth and so on, Piles transition, blah, 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 and momentum and pseudo-momentum of light. And in this chapter, he basically wrote about our results. Okay? So our results are now in that book, very nice. And most of the other people who contributed to these surprises were really quite famous people, so we were in very good company. It makes us very happy. Unfortunately, he was rather old at that time and he no longer had a secretary. So when he wrote the name of my colleague live, it was handwriting in those days, no computer. Didn't write it very well, so it came out printed as L-A-L rather than L-A-I.
When was this book? When was this book published?
This book? Not many years after our work. 80s, mid-80s. So now, so if you look at this, you see this is the term that is important for the optical tweezers. It says that the force has a term which is the gradient of the potential. Okay, so the square bracket goes as E squared. The force goes as gradient of E squared. If you call that as negative gradient of the potential energy, then the potential energy is minus something times U. So in other words, the part with large E square is a potential well. Things get attracted to a region of high E square. And that is the idea of
the optical tweezers. The plastic bead gets attracted to a region pi e squared, is small here.
What about the B square contribution?
That's a much smaller by an order of b over c squared. All right. Then that got us thinking about some other issues, about a general set of issues that I think is not yet completely fully understood in the following sense. Let's go back to thermal equilibrium. Suppose I have a bucket of water and I subject it to an inhomogeneous E field. And I ask, what is the equilibrium distribution, that bucket of water or gas? Okay? So I want to find the equilibrium configuration. So how do you do it? You maximize the entropy. Okay? That's how you do it. Or you minimize the free energy. Basically good. You go to many books, most books do it incorrectly. Although the final answer is correct, sort of correct. The only, among the classical texts, the only one that is absolutely careful and correct is in Landau and Lipschitz. Not classical theory of fields, electrodynamics of continuous media. And this is a smart guy. I mean, he absolutely knew what he was doing. He was very careful. So how do you do it? So you have a configuration. So what do? You imagine a virtual displacement. You imagine moving it a little bit. And you require that the first order variation in the entropy is 0. Basically that's right. But when there are long range forces like E field and B fields and gravity for that matter, there is a subtlety. Think about this. This is a special case. I do a virtual displacement, okay? I move this in or out and minimize energy, maximum entropy, and so on. I wrote down this energy, d squared over kappa or sigma squared over kappa, and you would think that larger kappa is lower energy. But that is only true if I hold d fixed. If I hold e fixed, what would you say? Instead of writing d squared over kappa, you would write kappa times e squared. And it would seem that smaller kappa is lower energy. Right? So you could get opposite conclusions. So do you hold d fixed or do you hold e fixed? Well, answer is neither. What do you do? Well, okay, let me be a little bit formal. So what do you do? Suppose you have, let's see how the usual argument goes. I have a system, I divide it into subsystem 1 and 2. So I vary the total entropy, want it to be 0. But in doing so, I have to satisfy two constraints. One is that the total energy should be unchanged. Okay, because I isolate the system. So I use a Lagrange multiplier to impose this constraint. And the total particle number should also be unchanged. So I use another Lagrange multiplier to impose that constraint. So that is the condition. You have to impose those conditions. So if you work it out, that tells you that 1 over T1 is beta and 1 over T2 is also beta. So T is uniform. So T1 equals T2 equals 1 over beta. Okay? And likewise, mu1 equals to mu2, and that's chemical potential. So, but when you have long-range forces, as I said, think about it. Suppose I have capacitors here, two capacitors, a gas here. As I move the gas around, E is not fixed, D is not fixed. Everything changes. But what is the constraint? The constraint is that whatever you do at every point, divergence D has to be unchanged. Because if that's equal to the free charge, and you're not moving the free charge. Curl E has to be unchanged, because that's always 0, I mean, doing statics. So that is two constraints at each point in space. At each point, I want this black guy to be 0 and that black guy to be 0. So at each point, I introduce two Lagrange multipliers. So these are local Lagrange multipliers enforcing the field equation at each point. So E and D are free variables but subject to constraints. Okay? So I don't require E to be fixed. I don't require D to be fixed, but I require divergence D to be fixed. I require curl E to be fixed. So I have this whole bunch of local Lagrange multipliers. And if you work this out, it's no longer obvious that the temperature will be uniform. If you look at it, once you, why is that the case? You see, the dielectric constant has some, depends on temperature, there's some equation to stick. Okay? So as you vary the temperature, there's an extra term coming from partial derivative of this guy with respect to temperature and so on. So temperature appears some extra terms, extraneous terms, and it's not entirely obvious that your conclusion will be that the temperature is uniform. But it turns out, in this case of dielectrics, all the extraneous terms happily cancel. That's a bit surprising. Okay? And temperature is uniform, everything is fine. Now, it's surprising and it's not surprising in the following sense. It's surprising because the dielectric constant appears and that has a temperature dependence. But I can take another point of view. I don't have a dielectric, I just have a bunch of dipoles in which there is no phenomenological dielectric constant, so there's no temperature dependence. So that should work out. So if the two descriptions are to be consistent, I must get temperature constant. So temperature affects energy and so on. But suppose I generalize this to gravity. I do the same thing with gravity. Roughly speaking, Laplacian of the gravitational potential has to be equal to mass density. Okay? So I enforce that, that equation with local Lagrange multipliers. It turns out we found something to our great surprise, that in such a long-range system with gravity, where the source of gravity is not just the mass density, but the energy density. Okay? So if you heat up a piece of a part of the gas, the kinetic energy increases of the gas. So even the energy divided by c squared is a source of gravity. So the gravitational interaction increases. Through that term, it turns out you find the result is that for such a system in thermodynamic equilibrium, temperature is not uniform. Which is sort of like a violation of what? The zero law of thermodynamics. Okay? And that shocked us no end until we found that this result again was not novel, was known to Thoman. You know this thick book by Thoman, relativistic something or other, relativistic cosmology. Yeah, actually in one section, in the general relativistic case, he proved exactly this result. But his proof was in the context of a spherically symmetric general relativistic thing with the Schwarzschild metric and so on. But actually you don't need that. All you need is to impose these local constraints and you get this result. And it is exactly parallel to the problem of forces in a dielectric and the equilibrium.
How much the variation of the temperature?
Essentially phi over c squared, where phi is the Newtonian potential.
So it could,
Very small.
Have you studied this in like astrophysical object like neutron star? Or?
Yeah, but neutron stars are not never in really thermal equilibrium.
Okay.
If you can get a neutron star to be really nicely in thermal equilibrium, you should see.
That could still have some effect on
those
systems. Right. This is another.
Okay, but heuristically, these are the same things because energy is something that responds to the gravitational field. It likes a region with strong gravitational fields. So energy, in addition to the usual Boltzmann factor, likes to go to the region of higher fields. And where energy goes, that's the temperature. Okay? And that is why there is a tiny effect, tiny phi over c squared, but actually conceptually quite curious. And this phenomena is basically the same idea as for a dielectric, because dielectric is something that responds to electric fields, and it likes region of strong electric fields. And this effect, that a dielectric likes to go to a region of high electric field, is the conceptual basis of optical tweezers. That is why it gets attracted to there. And it is connected to this general framework of trying to understand how you describe the equilibrium or maximum entropy configuration of a system under long-range forces. So the whole idea of equilibrium, thermal equilibrium in the presence of long-range forces is not, I claim, not fully well understood. Let me repeat this point because I think it's important. If you go back to your StatNet textbooks, the usual discussion is this. You take a system, you divide it into subsystems, let's say 2, and you imagine moving some energy from here to here and so on, okay? And everything is just additive. Energy plus energy, entropy plus entropy, and so on. And that's how you obtain everything. And the reason you can do that is because this part has nothing to do with this part, except for a thin layer at the interface, because all interactions are short range. And in the macroscopic limit, that thin layer can be neglected. But if there are long-range forces, if I move something from here to here, say move dielectrics, that will affect the electric field even there. And things are no longer simply additive. And all the textbooks descriptions fall apart unless you impose all the constraints enforcing the fact that every piece is connected to every other piece through the long-range forces. And it's not just adding up the energy and so on. You have to look at all these correlations and mathematically impose them, describe them with these local Lagrange multipliers. That is only a mathematical description, but the point is you can no longer think of a large system as the sum of independent units linked only by total energy and total this, that, and the other. There are long-range correlations. Yeah?
Is there a problem if I can only define the Boltzmann distribution locally?
Yeah.
Is there a problem for that? Or
No. You describe. No, locally you can always describe.
I mean, because T is not uniform, so exponential minus beta is not uniform.
No, wait. If you take a thermodynamic description,
Yes.
I don't even know about Boltzmann distribution.
So in here, is there a Boltzmann distribution?
Yeah, it is, but I can discuss this whole thing without talking about Boltzmann distribution. It's just that partial S over partial U is the same for every subsystem. Okay? I'm not even talking about how the molecules or atoms are distributed within each subsystem. Okay? Okay, so that's really what I want to say, and I hope I've given you a broad overview of a number of topics, all having to do with how a long-range force, electromagnetic in the case of Ashkin, interacts with particles, the effective potential, and some of the attendant theoretical subtleties. Thank you.
We thank Professor Yang for a very rather educative talk, which is inspiring for the audience. Now the talk is open for discussion.也可以用中文问哈，那个杨教授的中文也非常好。
这个 less
我不太懂，最后说 long range force 就是
你没听到
long range force
呀？
就是那个为什么过程会那么重要？就是它不是都可以直接叠加？
我还没完全听懂。Louder please。
哦，就我不太懂为什么就是过程那个 long range force 在研究的时候，它那个移动的过程那么重要，因为它不是最终都是叠加的结果。
不是。Okay, let me say that once more. Normally, when you try to determine the equilibrium configuration by requiring the entropy to be maximum, let's say, okay? So what does that mean? you consider a virtual displacement, and you say variation of entropy is equal to 0, the first order. And the entropy, you can do things independently. Now, what are the independent variables for a system? Normally you say density and temperature of each subsystem. That completely describes the system. When there are long-range forces, that's not enough. You also need to tell me the electric field everywhere, or the potential, doesn't it? Let's say electric field. So for each small piece, I need density, temperature, and electric field. So I need electric field here, electric field here, electric field here, everywhere. Now, but then once I add the electric field, that is an over-prescription. I cannot arbitrarily assign electric fields at every point. Whatever I assign must satisfy, for example, curl E equal to 0. Okay? So on the one hand, you need to add the fields. On the other hand, adding all the fields is over-description. So I need to add a constraint. The constraint is that curl E is equal to 0 everywhere. Okay? And that constraint is not 100% local because it involves a spatial derivative. So once you need to add that constraint, the usual textbook discussions become invalid. To put it less mathematically, it means what you do here and what you do there are not completely independent because they are linked by a long-range interaction. Whereas usually you try to make independent variations in different places. Okay? So any interaction that vanishes like 1 over r cubed or slower, you have to worry about this.
So the last part, if there's no gravitational field, then you don't see the non-uniform temperature dependence, right?
Right.
So why gravitational field plays a role that's somehow make the temperature not uniform?
Okay. You can approach this in many different ways. The way people usually describe the Tolman result before we did it using variation is the following. Suppose you have this room and the room upstairs is in thermal equilibrium. Okay? So you have thermal equilibrium means you have black body distribution here of photons. Take one of these photons and suppose it climbs up. It gets redshifted by gravitation or redshift. Okay? So and when it gets up there, it's in equilibrium with the distribution there. Then that temperature must be different from this temperature by a Doppler shift. It's basically the Pound-Repka effect. Okay, so the Boltzmann distribution here of photons and the Boltzmann distribution upstairs must differ by that gravitational redshift. So they have a different temperature.
So basically, in different frame, I see different energy. So I define
It's
the
not
temperature.
different frame. I'm not doing there's no relative motion.
I mean,
It's a gravitational redshift.
okay.
So it's a gravitational redshift. I mean, temperature is just sort of energy. So gravitational redshift is also redshift of temperature. That's a naive way of saying it.
Any other questions?
The question is maybe technical, maybe that's better to reserve it for later. But let me ask now. If you think of let's say a QED vacuum, the the vacuum has a dielectric constant coming from contribution of matter and stuff. Do you think that could this effect you describe is for material system, the optical twister effect? Would there be something like vacuum effect, like Casimir effect, due to high electric field, which somehow squeeze? I don't know what would the manifestation of that.
But you need an inhomogeneity in the E square. Now you just have vacuum. It's like a dielectric. But it's a uniform one.
Vacuum, and then I present in some laser with some. I don't know what could be the there should be something, but I don't know what would be observable.
Yeah, I don't. Well, you have to. This is not nearly as fancy as a Casimir effect because the whole idea of dielectric is something very phenomenological.
Yeah.
It's not anything fundamental, right?
No, but if one can generalize it and think about the same.
I can't answer this question.
We can think of it more.
Yeah.
Any other question? If not, then let's thank Professor Young again.